All right, welcome back, everyone. Today we're going deep on something that you might not think about too much, but it's super important.
Yeah.
It's like the heartbeat of all our gadgets. We're talking about clocking architecture in systems on a chip.
Right. The brains of pretty much every device we use.
Yeah, smartphones, computers, you name it.
Even spacecraft.
Oh, yeah. And our guide for this deep dive, a fascinating research article.
It's a good one.
So we're going to be talking about nanosecond precision across an entire chip. I mean, just think about that for a second.
It's mind-boggling when you really consider it.
Absolutely. What could possibly go wrong?
Well, to be honest, quite a bit can go wrong. Any inconsistency in these clock signals, we call that jitter, can lead to some, well, pretty major problem.
Oh, I bet. Give me an example.
Sure. Imagine like a high-speed data transfer going along, and then bam, it gets all garbled because the timing's off by a tiny bit.
We're talking like a fraction of a second.
Even less. We're talking picoseconds. It's like, imagine a beautiful piece of music, and suddenly there's a note just off.
Ouch, that ruined the whole thing. Okay, so now I'm starting to get a sense of just how high the stakes are here, but let's back up a bit. How are these clock signals even generated on a chip in the first place? Where do they come from?
So there are two main approaches. One way is to use what we call an external clock, and this relies on an off-chip crystal resonator.
Okay.
They're known for being really accurate and stable, but they do add to the cost and the size of the whole system.
So it's kind of like, if I think about it like a watch, it'd be like a high-end, super accurate watch. Great for precision, but maybe not for every situation, right?
That's a great analogy. The other option is an internal clock, which uses an on-chip oscillator.
Okay.
Now, these oscillators might not be as accurate as those external clocks, but they have their advantages.
Like what?
Well, for one, they consume less power.
Makes sense.
And two, they take up a lot less space on the chip. Ultimately, it really comes down to a classic engineering trade-off, weighing those factors against the performance needs of a specific application.
So you wouldn't use the same type of clock for, say, a high-performance gaming system versus a tiny sensor in a wearable, right?
Exactly. You need to pick the right tool for the job.
Okay, this is making me think about, like, wearables, for instance, like a smartwatch or something. Battery life is so important in those devices.
Oh, absolutely.
So I'm guessing an internal clock would be the preferred choice there, right?
Well, you're spot on. Minimizing power consumption is key in a smartwatch, so a low-power internal clock would definitely be a better fit.
Got it. Okay, so we have these clocks, either internal or external, generating the base signal. But the research article talks about managing these clocks and creating all sorts of different signals that are needed across the entire chip. And it mentions these things called phase-locked loops, PLLs.
Yeah, PLLs are essential.
They'd sound kind of like the central nervous system of the whole operation.
That's a great way to put it. A PLL takes that reference frequency and manipulates it, it multiplies it, divides it, fine-tunes it, and the result is all the different clock signals that the various components on the chip need to function.
So it's basically like a signal processing engine, customizing the clock for each part of the SoC.
Exactly. It's tailoring the beat for each instrument in the orchestra.
Okay, I'm following you. And it's not just a one-size-fits-all situation, right? The article mentioned specialized PLLs.
You got it.
So what makes those different? Why do you need specialized PLLs?
So specialized PLLs, they're all about addressing very specific performance needs.
Okay.
For example, you might need a PLL that prioritizes ultra-low jitter that's essential for things like high-speed data transfer.
Where even the tiniest timing error could be a disaster.
Exactly. Or, on the other hand, you might need a PLL that really focuses on minimal power consumption, say for a low-power sensor.
Right, like for that smartwatch we were just talking about.
Precisely. And there's a lot of exciting research and development happening in this area to create PLLs for all sorts of specialized needs.
Speaking of which, the article specifically called out a company called Silicon Creations as a leader in this field.
Oh, yeah. They're doing some really impressive work.
What stood out to you about their approach to PLLs?
Well, what's really cool is that they design these specialized PLLs, right? They design PLLs for a whole range of applications, and they're really tackling those trade-offs we talked about, between performance and power and size.
So it's like they have a toolbox full of different PLLs, each one optimized for a specific task.
Yeah. That's a good way to think about it.
So give me some examples. What kind of specialized PLLs are they creating?
Well, they have this low jitter PLL, and it achieves sub-picosecond accuracy.
Wow, sub-picosecond. That's incredible.
Yeah, it's amazing. It's critical for high-frequency applications.
Right, like that high-speed interface we were talking about. We're talking about data corruption. If that clock signal isn't rock solid, that level of precision is pretty mind-blowing. What else? What other examples do they have?
Well, they've also developed this really cool LCPLL.
LCPOL, okay.
And get this. This achieves jitter levels in the hundreds of femtoseconds.
Hundreds of femtosecond. I mean, come on, are you kidding me? That's like unimaginably small.
I know. And it's essential for things like sensitive radio communications.
Right, where signal purity is everything.
Exactly. You need a super clean, precise clock signal for those applications.
This is so cool.
It is. And they've got something on the other end of the spectrum, too, a low bandwidth PLL. This one is designed for ultra-low power consumption.
I'm guessing that's perfect for those battery-powered devices.
Absolutely. Things like IoT devices, wearables, anything where every microwatt counts.
So they really are covering the whole spectrum of needs with these specialized PLLs.
They are. They really are. It's fascinating stuff.
It is. But let's go back to something you mentioned earlier, jitter. I want to make sure I really understand this. Break it down for me. Why is jitter such a big deal, and what actually causes it?
Okay, so think of jitter as basically any unwanted deviation in the timing of that clock signal.
Okay.
And even tiny variations, and we are talking tiny picoseconds or even femtoseconds, can really mess things up.
So anything that throws off that perfect rhythm can cause problems.
Exactly. And, there are a lot of things that can cause it. Noise from the power supplies, variations in temperature, even limitations in the PLL itself, you name it.
It sounds like as devices get more complex and we push for higher and higher performance, jitter becomes an even bigger headache.
Oh, absolutely. It's one of the biggest challenges for designers.
So how are they dealing with it? What are the solutions?
Well, that's what's so fascinating about companies like Silicon Creations. They've actually developed something called a jitter monitor IP.
Okay.
And this allows for on-chip jitter measurement in real time.
Wait a minute. They can actually measure jitter while the chip is running?
Yep, that's right.
How does that work?
Well, they integrate this jitter monitor IP right onto the chip itself. And this allows them to constantly monitor the clock signal, looking for any deviations, no matter how small.
So it's like having a built-in diagnostic tool.
Exactly. It helps ensure that the clocking system is performing as expected, even in the most demanding applications.
That makes a lot of sense. I can see how that would be valuable during the design phase too, right?
Absolutely. Engineers can use the jitter monitor to identify and address potential jitter issues early on, which ultimately leads to more robust and reliable systems.
So they're not just building these incredibly precise clocks, they're also giving engineers the tools to keep them running smoothly.
It's a pretty ingenious approach, really.
It is. I'm really curious to learn more about this whole dynamic between performance, power, and jitter. Can you give me a specific example of how those factors all come into play when designing a clocking system?
Sure. Let's say you're designing the clocking system for a high-performance processor, like in a smartphone.
Okay.
You need a clock signal with incredibly low jitter.
Right, for smooth and reliable operation at high frequencies.
Exactly. But at the same time, you also need to keep power consumption in check.
Especially if you want that phone to have decent battery life.
Right. You can't just crank up the performance to minimize jitter and then have the battery die in a couple of hours.
So how do designers find that balance? It sounds like walking a tightrope.
It is. It takes careful planning and optimization. It really comes down to making smart choices at every step of the way.
So give me an example. What kind of choices would a designer have to make?
Well, for instance, they might choose an LCPLL for its low jitter characteristics, which would be great for performance, but then they'd need to carefully design the circuitry around it to make sure it's not using too much power.
So it's this constant back and forth trying to squeeze out the best performance while also keeping power consumption in check. Sounds like a pretty complex puzzle.
Oh, it definitely is. And that puzzle gets even more complicated as we shrink down to smaller and smaller transistors.
Which brings up something I wanted to ask you about. The impact of technology scaling on clocking design. The article mentioned TSMC's N3 and Samsung's 3nm processes.
Right, those are the cutting-edge processes.
What kind of hurdles do those advancements create for clocking systems?
So as transistors shrink and operating frequencies increase, noise becomes a much bigger problem.
So it's like trying to maintain a perfect rhythm in a room that's getting louder and more chaotic.
That's a good way to put it. And of course, power consumption is always a concern, especially as we try to cram more and more functionality into smaller and smaller devices.
So it sounds like it's a never-ending race. Chip designers are constantly having to come up with more sophisticated clocking solutions to keep up with the advancements in chip technology.
That's exactly right. And it's one of the reasons why companies like Silicon Creations are so important. They're at the forefront of this innovation, developing new architectures and techniques to address the challenges of clocking in these incredibly advanced systems. You know what really struck me in this research article?
What's that?
It's not just about raw performance anymore. It's more about creating these really specialized solutions that target very, very specific needs within a chip.
That's right. We were talking about Silicon Creations and their approach, and it's almost like they have this toolbox full of different PLLs, each one tuned for a different job.
Exactly. It's not a one-size-fits-all situation anymore.
And that makes sense when you think about it. I mean, different parts of a chip, they probably have totally different needs.
Oh, absolutely. You could have a high-speed data interface that needs an incredibly low jitter clock right next to a sensor that needs to be super power efficient.
Right. You don't want that sensor draining the battery. Okay, so walk me through some of these specialized PLLs. What kind of innovations are we seeing that address these different needs?
Well, think about things like phase alignment and skew compensation.
Okay.
As chips become more complex, you need to make sure that different parts are getting their clock signals at the right time, even if they're physically far apart on the chip.
Oh, I see. So it's not just about keeping time, it's about keeping everything perfectly in sync across the entire chip. And I imagine that becomes even more important at higher frequencies.
Exactly. You're absolutely right. And Silicon Creations, they've actually developed some really interesting solutions for this. They have something called a DESQ PLL.
DESQ PLL. Okay.
And this can compensate for the timing differences between different parts of the chip. Think of it like, in an orchestra, you have the conductor who can adjust the tempo for different sections, keeping everything in harmony.
Oh, I love that analogy. Okay, so this DESQ PLL is basically correcting for the delays that happen as the clock signal travels across the chip.
Exactly. They've also got something called a digital phase aligner. It's an IP block that can fine-tune the phase alignment of the clocks.
So even more precise control over the timing.
Yeah, it allows for amazingly precise control. It makes sure everything is synced up perfectly.
This is incredible. So they're really hitting this problem from different angles, not just focusing on the PLL itself, but building in these additional tools to fine-tune the timing across the whole system.
Exactly. And they've even developed a technique for distributing the clock signal that minimizes variations in load capacitance.
Load capacitance, okay.
That's a common source of jitter.
Yeah.
And by managing how the clock is routed and buffered, they can actually reduce the jitter even further.
Oh, wow. So it's a really holistic approach. They're optimizing not just the PLL, but the whole clock distribution network.
Exactly. It's really fascinating how much detail goes into all of this.
It really is. It makes you appreciate all the engineering that goes into something we usually never even think about. I mean, every time we use our phones or our computers, there's this crazy dance of signals happening at super high speeds, and it's all orchestrated by these tiny clocking systems.
I know. And, as we move towards even smaller technology nodes like the 3-nanometer processes from TSMC and Samsung, it only gets more complex.
Right, those next-gen chips. So what does the future hold for SoC clocking architecture? How do we keep up with these demands for more and more performance?
That's the big question. The research article, it pointed to some potential areas for the future. One thing that stood out to me was the continued development of LCPLLs.
Right, the ones with the super low jitter performance.
Exactly. They're already achieving jitter levels in the hundreds of femtoseconds, which is just amazing. And researchers are trying to push those limits even further.
Wow. It's like this never-ending quest for the perfect timekeeper, always striving for better precision, better stability.
It really is. And these advancements in clocking, they're paving the way for even more powerful and sophisticated devices, things we can't even imagine today.
This has been such an incredible journey, diving deep into this world of SoC clocking. I feel like I've learned so much.
Me too. It really is an incredible field with so much innovation happening behind the scenes.
And, as we've been going through all this, it's really made me think about how much we're relying on this clocking technology. We don't even realize it's there.
Yeah, it's true. It's like it's the heartbeat of all our devices.
Yeah, and it's just constantly evolving, getting more and more precise. I mean, we've been talking about picoseconds and femtoseconds. Those are like incredibly small amounts of time.
Yeah, and even those tiny, tiny differences, they have a huge impact on how well our gadgets work.
Right, like how even the slightest jitter can mess up things like high-speed data transfer.
Exactly. And we talked about sensitive signals, too. Jitter can really degrade
It's
those.
like a domino effect, right? One tiny timing error can lead to a whole bunch of
Yeah,
problems.
it can cascade through the whole system.
And as we create even more complex applications like AI and superfast networks, that precision is only going to become more important.
Absolutely.
So it makes me wonder about the future of computing, with Moore's Law and all that.
Yeah.
As we squeeze more and more transistors onto these chips, how do we make sure the clocking can keep up?
Well, that's the big question researchers are working on right now. One area that seems promising is developing new materials and processes.
Okay, how would that help?
Well, the goal is to minimize the noise and the variations in that clock signal.
So it's not just about designing fancier PLLs, it's about actually addressing the physics behind it all.
Right, exactly. And there's also a lot of really cool research going on looking at ways to create what they call intelligent clocking systems.
What are those?
So imagine a system that can actually adjust its frequency or phase on the fly based on what the chip is doing at that moment.
Wow, so it's like super adaptable.
Yeah, it makes sure every component is getting the exact timing it needs, no matter what.
That's like a conductor who can not only keep the orchestra in sync, but also change the music to fit the mood of the audience.
Aha! That's a great way to put it.
It sounds like we're going to see some pretty amazing advancements in the next few years.
Oh, I think so. And with those advancements, who knows what kind of new possibilities we'll unlock.
It's pretty exciting to think about. Well, this has been an amazing journey into this world of SoC clocking architecture.
It really has.
I definitely have a whole new appreciation for all the complexity and the ingenuity that goes into this technology that we usually don't even think about.
I agree. It's really impressive what engineers and researchers are accomplishing in this field.
And to all our listeners, we hope you've enjoyed this deep dive too. Next time you pick up your phone or really use any gadget, take a minute to think about that intricate dance of signals happening inside, all thanks to these tiny but super powerful timekeepers. Until next time, keep exploring.